A warm welcome to today's webinar. The webinar is organized by the New Zealand Stainless Steel Development Association, the University of Canterbury in Christchurch, supported by the Steel Construction Institute, and conducted by the International Molybdenum Association and the Nickel Institute. It covers the topic Stainless Steel Reinforcing Bar. Today's presenter is Dr. Catherine Cashel, Associate Professor in Structural Engineering and Design at the University College London. Our panelists of today are Ms. Nancy Badu, Associate Director of the Steel Construction Institute, Dr. Ke Tsiang, Lecturer in Structural Engineering at the University of Canterbury in Christchurch, and Paul Geppert, Executive Director of the New Zealand Stainless Steel Development Association. I'm your host today, Jörg Schweitzer, Manager Market Development in Southeast Asia. With this, I would like to wish you all a very interesting webinar. Over to you, Catherine.
And good morning, everybody. I have to work at saying good morning because it's 9 p.m. in London, where I'm coming to you from this evening. And I'm sure quite a bit colder than it is where you are. So it's a pleasure to be here. It's a pleasure to talk to you this morning. I'm going to talk about stainless steel reinforcement in concrete structures. So first, I'm going to give, this is just an overview of the presentation that we're going to give this evening. I'll start with a little bit of an introduction and some background to myself and how I ended up, well, ultimately being here this morning with you, but working in the field that I work in. And then we'll go into the stainless steel rebar a little bit more and the motivation for use, where it's being used, how we can use design codes to use it and where the gaps there are. Some applications and developments that have happened over the last 30 years or so. We'll have a look at product availability, some research and recent research developments, and then the future opportunities and needs, I guess, which are plentiful in this particular topic. And then we'll bring some concluding remarks before the question and answer. Okay, so starting with a little bit of an introduction. I just had a nice introduction from Jörg, so I won't dwell on this too much. But I just want to highlight, this is a little bit of a mini CV of me. And the second point there is I spent a couple of years working with Nancy, who you've all hopefully heard a lot of good stuff from over the last couple of weeks at the SCI. And that was where I really started to work with stainless steel with Nancy and learn the material. It was much more from a structural stainless steel, bare stainless steel point of view, which I know was the topic of the last couple of weeks of the webinars. And it was really only in very recent years that we have started to delve a little bit more into rebar. And I currently work at UCL, as we've said before. So just my own research background, I guess, and the topics that I spend a lot of time thinking about. My real background is in steel and composite structures, with a particular focus on structural fire engineering, a lot of testing, a lot of numerical analysis, design methods. And like I said, in more recent years, we've started to do a lot more work into different types of materials, particularly stainless steel, but also high strength steels, FRPs, new shapes, anything really which can try to lower the carbon footprint of the structures that we're designing. And stainless steel has a big role to play in that particular endeavor. I'm going to put this out here straight away. What I am not is a corrosion expert. I am absolutely not someone who knows a huge amount about corrosion in any context, dare I say it, and particularly the different types of corrosion, and this can be quite a complex subject for bare stainless steel, but also for rebar. But we'll touch a little bit more on that as we go through today's presentation. I put this slide up just because I think it provides quite a nice background to to the motivation for a lot of my research, including that on stainless steel, which is this dream, I guess, pipe dream to try to create more sustainable and resilient structures. So like I said, a lot of my own work focuses on fire behavior. I know that's a very vibrant research area also in New Zealand. And coupled with that is another dream, which is to try to create a more sustainable built environment. And often those two things, the sustainability and the resilience under extreme loading conditions, those two targets can be quite conflicting, in the sense that often our way of making something more resilient is to use more material, which of course is unsustainable. So it is in that context really that materials like stainless steel have a very important role to play, because they can achieve both things when used appropriately. But of course, we need a lot of research and data in order to enable us to use it effectively and efficiently. I quite like this quote, which is why I included it here, which says that in a future of scarce raw materials and an energy crisis, it is both uneconomical and irresponsible to employ materials other than those which offer the maximum potential. So I think that's where I come at my research for stainless steel, which is that, of course, we're using a material which is a finite resource, but if we use it carefully and effectively and efficiently, and we exploit all of its excellent characteristics in design, then it can lead to a better outcome. Okay, so moving a little bit more into the topic of the stainless steel reinforcement and the motivation for using stainless steel reinforcement. This is obviously the third session on stainless steel, Nancy having delivered the ones for the last couple of weeks. So most of you will now be aware of the major attributes of stainless steel as a material. Concrete, on the other hand, is well, I was going to say it's an unpopular material. That's actually obviously not true. It's a hugely popular material, but it's getting a bit of a bad reputation at the moment because, of course, it's not particularly sustainable. But it's the most used material globally for infrastructure projects. So it's a hugely important material in the context of the built environment. Corrosion of rebar in the structural concrete is a major problem for reinforced concrete structures. It's not just a structural problem, but it's also an economic problem. It obviously costs a lot of money to repair corroded steel in concrete structures, and it can have even bigger costs in an indirect way when things like bridges and other parts of infrastructure need to be closed for those repair works. So there's a real financial cost to the corrosion problem of rebar in concrete. As I say there, rehabilitation and strengthening is hugely expensive and can also require a lot of monitoring and maintenance ongoing during the life cycle of a structure. As a secondary issue, resilience of concrete structures is always under a lot of scrutiny, I guess. Ductility of concrete structures is very important, particularly under extreme loading scenarios. And I'm very conscious, obviously, speaking to a group of engineers in New Zealand, that you don't need me telling you about how important it is for our structures to have ductility. Efficient design is another motivation for using stainless steel reinforcement. So again, it's trying to get the very most out of our materials. When we do use materials, we need to use them effectively and efficiently. Here I have a couple of nice pictures, nice if you're that way inclined, nice pictures of scenarios where stainless steel reinforcement might have been a good idea. So we're looking here at coastal applications where there's been some degradation to the concrete and the rebar becomes exposed and of course rusts under that harsh environment. So repairing these sorts of structures or structural defects is hugely expensive, hugely difficult, but also very important for the infrastructure that they are providing. This is another picture which I include simply because I took it last year myself when I was on holiday in the Middle East. Found myself under a bridge one day, looked up a bridge that was over a river, and this was the rebar exposed under the bridge, which appalled me a little bit. But again, another nice example of where stainless steel reinforcement may have been a good option. This is an interesting picture. So this is another example or another application of where stainless steel rebar was used. So in the far side, the far right-hand side of this picture, you can see a pier, which was built in Mexico in 1941. So that's quite a long time ago, using 304 rebar, austenitic stainless steel rebar. And you can see that it is in really good condition. So however many years later, there's been no repairs required and very little to no maintenance needed. None of the structural concrete or rebar. Overall, this bridge, or pier rather, is thought to have cost around 50% of what a carbon steel alternative may have cost, taking the whole life costing into account. In the foreground of this photo, you can see the remnants of another pier, which was built much later, so in 1969, but using carbon steel. And you can see that, of course, that did not survive particularly long. So in terms of life cycle performance and life cycle cost and impact to the local environment, that could be viewed to be a little bit of a waste. And the stainless steel reinforced concrete pier is a much more effective and useful use of our resources. But this is quite a nice picture because it illustrates where stainless steel reinforcement has an important role to play. So a little bit of a recap. I know Nancy has covered a lot of this in the last couple of weeks, but a recap on some of the key advantages of stainless steel, not just stainless steel reinforcement, but stainless steel as a structural material. So we know a lot about the corrosion resistance. Of course, that's typically the primary reason that we choose to use stainless steel in structural applications. It also has excellent mechanical properties, so that's really good strength, outstanding ductility, which can be really important, good weldability, workability, and things like that. Excellent fire resistance, so it tends to behave a bit better than carbon steel during a fire event. A very long life cycle, which is of course linked to the durability. Fully recyclable when it's bare. Stainless steel, of course, that's a bit trickier for rebar. And reusable. I have those ones highlighted because they're less relevant to the reinforced concrete. Of course, it's available in lots of different grades, and that is sometimes viewed as a bit of a challenge for stainless steel because there are so many grades that really some good guidance is needed for designers on where to start. But equally, it means that there's a solution for almost every problem and that we can maximize the exploitation again of the qualities of a particular grade in a particular application. A little bit on the cost, because that's obviously often seen as a prohibitive factor in the specification of stainless steel. It is expensive compared with carbon steel, but of course that's only when we take into account the initial costs. It can cut up to 50% of the overall maintenance costs through the service life of a structure and can increase the life cycle, so the length that our structures can remain in service. And that's a really important factor given the climate crisis that we're currently living in. So why would you use stainless steel reinforcement? So again, the obvious one is the corrosion resistance, but drilling into that a little bit further, carbon steel reinforcement obviously corrodes when exposed, but when it does corrode, the volume of it can increase by up to 10 times the original cross-sectional volume, which can cause cracking and surface staining in the surrounding concrete. This, of course, means that more water gets in, the oxygen and the chlorides can accelerate the attack on the steel, which further propagates the problem. This can lead to concrete spalling, further corrosion, and ultimately and potentially structural failure. On the other hand, of course, stainless steel reinforcement doesn't corrode typically, and its inherent corrosion resistance, even when exposed to chlorides in concrete, is what makes it so valuable for this application. There are other measures for tackling the corrosion problem in reinforced concrete. But studies have shown that using stainless steel as a reinforcement can provide a better long-term solution than galvanized rebars, for example. It's easier to manage and install compared with epoxy-coated rebars. Cathodic protection is another typical solution that's used to avoid the corrosion problem in reinforced concrete. And this can be effective, but it does also come with some challenges, such as that the reinforcement needs to be continuous, and it requires regular monitoring and maintenance, which again is costly in terms of resources. So in summary, the arguments for using stainless steel rebars are its durability, which is, I guess, the most obvious one. Its longevity is really important. Potentially the possibility to reduce concrete cover, which of course can then reduce the amount of concrete that we need. It reduces the weight of our structures. Increasing the ductility of reinforced concrete members. So this is something that we can really exploit with stainless steel, is that really high level of strain hardening that we get in the material. So using that in design is of value. Reducing the maximum design crack width, which is an interesting one, because then you have to ask, but do we care about crack widths when you're designing with stainless steel rebar? I guess from a deflection point of view and a serviceability point of view, we'll always care about crack widths, but they certainly become less of a driving force when you've got stainless steel reinforcement. Eliminating the costs associated with coating of the rebars and cement inhibitors and so on. And the last one is really important, so extending the life and minimizing the need for ongoing costs and use of resources during the lifetime of a structure. So I think the arguments for using stainless steel rebar are hopefully there and clear, which brings us on to the next part of our talk, which is looking at some of the codified provisions and developments. And before I get too into this, I'm going to, manage your expectations by saying there's very, very little in the codes about stainless steel reinforcement. So it is really still quite a new topic, and lots of the things that I've mentioned so far are semi-obvious, but we're still lacking a lot of performance data, which would be required in order to incorporate these things into our design codes. So the design codes as they stand really started from a structural point of view in the 1980s. So during that decade in the United States, many of the infrastructure, so reinforced concrete highway bridges, suffered from severe reinforcement corrosion, and many of the bridges actually failed. And this exact observation also occurred in the UK. And in the UK then, as things started to develop, in the 1990s, there was a revision to this document that's listed on your screen, BA 8402, which is the design manual for roads and bridges. And for the first time, stainless steel reinforcement was included in that design guide. And it required stainless steel reinforcement to be used around slab penetrations, splash zones, particularly in bridges, or wherever severe disruption would occur if the carbon steel corroded. Interestingly, it also allowed for some relaxed durability requirements, so lower cover, 30 millimeters rather than 50 millimeters as was standard for the carbon steel, and wider cracks were also permitted. So there was a relaxation in some of the durability requirements. Coming from where we're at now, which I'll go into in a little bit more detail in future slides, I'm uncertain as to where those limits came from or what the background for them was. But nevertheless, I guess it shows the faith in the performance of stainless steel reinforcement and its durability. So moving on to international design standards. So your own design standard in New Zealand for concrete structures, 3101, does not include any provision for stainless steel rebar. And perhaps someone on the webinar might be able to tell me different, but I'm unsure if there's any plans for it to be included or if it's on the radar at all. Eurocode 2, we're currently undergoing what's called the second generation of the Eurocodes. That's the whole suite of the European design standards. And the new edition, which should be out in the next year or two, it's not the fastest moving operation, will include some design recommendations for stainless steel reinforcement as an additional amendment to the main Eurocode. Also, FRP reinforcement will be included in that. So that's quite a step forward in the design context. I'm just putting in it here a couple of the key provisions that will be included for stainless steel reinforcement. I must say they're not particularly different to those for carbon steel. And that's mainly owing to a lack of data and a lack of performance data and reliability studies, as this is still quite a new topic. So the strength classes as provided are exactly the same as they are for carbon steel, as are the ductility classes. So the way that the material is qualified is very similar, is the same, in fact, as it is for carbon steel in Eurocode 2, which is, as I say, the European design standard for concrete structures. So this is the official name of Eurocode 2, EN 1992, and it is yet to be published, but it will include Annex Q, which is a normative annex, which is dedicated completely to stainless steel reinforcement. Interestingly, in terms of the material mechanical properties, as I said, they're all exactly the same for stainless steel as they are for carbon steel, except for a couple of things. So number one is fatigue. So in terms of fatigue, again, owing primarily to a lack of any, or at least sufficient test data and research on this topic, the code states that while carbon steel must pass a test during 2 million cycles, stainless steel is required to pass 5 million cycles. So testing to a more extreme limit owing to the lack of performance data. And the values for stainless steel are only given for that B500 strength class of rebar. On the ductility side, of course, we know that stainless steel is a very ductile material, and therefore, although it must fulfill the same values of the ductility classes as given for carbon steel for design, the ratio of the 7% strength to the 0.2% proof strength is used rather than the tensile strength as it would be for carbon steel. So there's a little bit of allowance made for the ductility of the material. But again, I think we're all aware, those of us that work in stainless steel, that this is underplaying the potential that stainless steel has in terms of its strain hardening. Young's modulus is given as 200,000 newtons per millimeter squared, depending on the alloy. So there's actually quite a big variation, which is something that we're currently looking into, going from 150 to 200,000 megapascals or newtons per millimeter squared, which is a much bigger range than it would be for the bare stainless steel sections. All of the detailing requirements in the code, such as anchorage and laps, are identical to those for carbon steel, and the cover is the same as carbon steel. So again, these two are owing primarily to a lack of performance data. And I'll say a little bit more about some more recent research in later slides on these topics. So barriers to using stainless steel rebars, the main barriers are perceptions of cost, issues around, questions again around galvanic acceleration of corrosion. So can it be used together with carbon steel rebars, for example? And actually research has shown that yes, it can be, that there's no galvanic acceleration of the carbon steel corrosion when it is used together with stainless steel. Product forms, availability, and questions around the chloride resistance. Again, these are the primary barriers to using stainless steel rebars. So moving on a little bit, and I'll fly through the next few slides, but looking at a few applications and developments. So the typical applications, as you might imagine, are highway bridges, parking garages, piers, coastal buildings, and so on. Here I just have some images of where it's been used. So we have Stonecutters Bridge in Hong Kong, which used grade 2205 duplex stainless steel rebar. And in many applications, it's selective use. So stainless steel is often only used in the splash zones, or it's only used in the part of the structure which are susceptible to corrosion. So it's often used together with carbon steel rebar. Here we have a bridge, which I'm not going to attempt to name, Schaffhausen maybe, bridge in Switzerland, which used 15 tons of stainless steel rebar, and interestingly saved 13% of the life cycle cost over an 80-year design life. So really, when the life cycle cost is taken into account, then stainless steel rebar packs a very decent punch. A couple of applications, not quite in New Zealand, but a bit closer to home. Here we have a bridge in Brisbane, which uses Lean Duplex 2101. And it was also used in the seawall in Sydney Harbour. And that was a rehabilitation. So very briefly, I've covered a lot of this already, but just kind of summarize some of the developments over the last 30 years. In 1995, there was a basic British standard, material standard for rebar, but only included 2 grades. Now we have much more grades. So on the right-hand side of this table, you'll see the current status. The production was really quite niche 30 years ago, whereas now it's being produced by many producers. There was very limited data on atmospheric exposure, the effect of pH and alkalinity, and there's a little bit more information on this now. There were absolutely no design rules, and now there's limited design rules, but there's more research happening all the time, as we will discuss in a moment. Briefly on the chloride accumulation, this graph shows the accumulation of chlorides in concrete with depth and over time. And if we look at the next slide, which is an application of that same graph, this is just a very simple example, but if we take the example of a structure where the concrete cover is 40 millimeters and a design life of 100 years, the critical chloride concentration for carbon steel rebar is 0.6%. And we can see down at the bottom, these solid black lines down at the bottom, at 40 years, after a 40-year design life, that 0.6% has been very much exceeded by carbon steel reinforcement. On the other hand, if we move further up the y-axis, stainless steel rebar, which has a critical chloride concentration value of 6%, is not met at any point in the design life. So this is quite a generic example, and it is specific to this situation, but it shows I guess how resistant and resilient stainless steel reinforcement is to chloride penetration, and how that can extend the design life of structures. Again, taking a look at that critical chloride concentration. So here we have 316 on the top, and we can see that for the high pH values, which would be appropriate for an in-concrete situation, we get quite a high critical chloride concentration value, very high for 316, a little bit lower for 304. Carbon steel is down at the bottom in black, and it is much, much lower. And where all this gets us or results is that with stainless steel, we can use less concrete cover, potentially, less crack width and risks associated with crack widths, which then means less requirements for crack control. Okay, so moving on quickly to product availability and the available grades. And I must confess that I haven't got a huge amount of information on local to you in New Zealand, but I will just present a couple of slides on the different grades. So it's available generally in a number of austenitic grades and duplex grades. And actually, it is the grade 14362, which is in the middle of this table, which is the most commonly used grade of stainless steel specified in structures for rebar. So a duplex stainless steel, a lean duplex stainless steel. Just taking a screenshot here from a stainless steel supplier in the UK, and you can see that they say they supply 304, 316, and this duplex grade 4362, which is really the most popular one and the most used one in real applications. A quick look at some New Zealand suppliers, Ancon here, and they also provide very similar grades. I won't dwell on this because you can look it up yourselves, but it is an available product in New Zealand. The recent research findings I'm going to go through quite quickly. I believe these slides will be shared with you after the presentation, so you can take a closer look yourselves or contact me offline if you wish. But together with some of the researchers that I work with and PhD students, we've been looking quite a lot at trying to provide some of this performance data for stainless steel rebar. So looking at the mechanical behavior under normal and fire conditions, the bond behavior, which is so important, limitations on design rules, and looking at some new analysis methods also. So in terms of the stress-strain response here, we have a typical stress-strain response for carbon steel, which is the yellow and red, the less ductile materials, and we have two stainless steel, diameter 10 millimeter and 12 millimeters. So you can see it's got the strength, and it's really importantly got a lot more ductility compared with the carbon steel rebar. Taking a look at the bond, so that's so important, of course, for reinforced concrete structures. So that composite relationship that develops between the concrete and the rebar. So here we did some pull-out tests. Hopefully you can see it over on this side of the screen, the left, pulling rebars out of concrete and comparing a carbon steel and stainless steel identical sample. And generally what we found is that stainless steel doesn't develop as good bond as carbon steel, but it's not far off. And the reasons for that are to do with the rib shape and also potentially the surface condition of the rebars. So we took those bond tests, and I won't go through this in too much detail, but we've developed some new, not so much new rules, but we've compared the bond strength of the stainless steel with the European, so that's the Eurocode 2 bond rules, and stainless steel is still completely on the conservative side. So although it doesn't develop quite as high levels of bond strength as carbon steel, it is certainly still well above that which is required in design. We've also done some beam tests, so looking at the development of cracking and things like that, and different reinforcement ratios and cover distances. And generally, as you would expect, what we have found is just a lot more ductility, and failure does not occur at such an early stage for a stainless steel reinforced concrete member. Sorry, went a bit fast. So yes, we were looking again at doing some numerical analysis. So trying to really understand the important parameters, what is causing and forcing the developments of cracks and the increase in deflections and things like that. So using our experimental data to validate some numerical simulations. And we've had some really positive results from that. And using all that data, what we really wanted to work on is trying to, I said it at the beginning, but trying to come up with ways of exploiting the very positive attributes of stainless steel by using the strain hardening and using its strength and its ductility in design. And current design approaches, so certainly those in Eurocode 2 and in the New Zealand Code, don't allow for that exploitation of the strain hardening and the strength limits and things like that. So we've been trying to use, I think Nancy has, if she hasn't talked about it already, then next week's webinar will talk about this continuous strength method. So new design methods which can enhance the design, well, I guess come up with a more accurate design prediction for the capacity of sections using the real material properties of the stainless steel. And just focusing on the highlighted numbers here, we found that using that approach for stainless steel reinforced concrete provides a much more efficient prediction of the real capacity compared with using traditional design methods, which have been developed for carbon steel reinforcement. So just a summary of some of the key findings from our research studies. Generally, the capacity is higher for stainless steel reinforced concrete members, better ductility, a more non-linear, rounded, gradual response compared with carbon steel reinforced concrete. Current design expressions in the Eurocode are overly conservative for stainless steel reinforced concrete, and some of our new developed methods provide a less conservative, less scattered set of data. Cracking was really similar. So between the carbon steel and the stainless steel beams, the crack patterns and the developments of cracks and the deflections at which they developed were shown to be really similar. For the set of tests we looked at, the failure mode was actually different. So the stainless steel specimens tended to crush, the concrete crushed, whereas the bars ruptured in the carbon steel equivalent. So again, that's important for the ductility and the warning of failure. Deflections were a bit of an issue. So the stainless steel members did deflect further as they progressed through the response, but not as much as we actually anticipated. Still well within the allowable values. Again, we've looked a little bit as well at fire, so trying to understand the mechanical behavior, the retention of strength and stiffness when a concrete structure might experience a fire scenario, and a little bit on spalling, which I'll come to in a minute. So we've done some, this is just an image from some elevated temperature tests that we've done to try to understand the material properties. And here we can see some reinforced concrete members with carbon steel reinforcement and stainless steel reinforcement in fire. And you can see, hopefully from this, that the member with stainless steel reinforcement outlasted and performed much better than the carbon steel reinforced concrete member in that fire scenario. So the deflections were not so, were more, I guess they were greater, but of course in a fire scenario or any extreme scenario, it's really the survival of the element is of what's prime importance. And the stainless steel member outlasted the carbon steel member in this scenario. But there's a lot more work to be done, I would say, in that area. And we're also looking at spalling. So we've got some tests underway at the moment, together with another university in the UK, the University of Sheffield, looking again at whether or not the spalling behavior in concrete is different for stainless steel rebar compared with carbon steel reinforced concrete members. And the initial results are showing us that it's not that different. So there's no real issue. And just like with regular concrete, incorporating fibers into the mix can be very influential and positive for delaying spalling. Indeed, even for only 15 millimeters of cover, we still didn't have any signs of explosive spalling. So that was a very positive outcome from that study. Very briefly on the seismic behavior, I'm very conscious that this is obviously such an important issue for you all in New Zealand. There is a lot to be done in this area. I'm not going to pretend like we have that many answers. There's been a couple of sets of tests done. So this is an image from the reference given below on some tests done on concrete bridge piers with reinforced concrete, stainless steel reinforced concrete. Quite large scale testing. And there was another set of tests done more recently in Europe. And in summary, the outcomes of this research, and I think this is seen as a really good application for stainless steel reinforcement, again, owing to the ductility. There was more yield drift and drift at maximum force for the stainless steel reinforced concrete members compared with equivalent carbon steel. The maximum lateral force of the austenitic stainless steel reinforced concrete column was shown to be greater than for the duplex, which was quite interesting. At the end of the test, it was observed that there was a greater degree of concrete spalling for the carbon steel reinforced concrete member in compared to the stainless steel member, but this needs a lot more investigation. And the carbon steel column experienced fracture of the rebar, which obviously isn't particularly wanted, due to inelastic buckling, and that did not occur in the stainless steel reinforced concrete member. So there's a lot more, there's some very positive results there, which need a lot more exploration, but the early signs are that this can provide a really nice solution. So before I finish up, and I am nearly finished, a very brief word on some future opportunities and where the gaps are. There are loads of gaps in this topic. There's a lot of things, we see a lot of potential, but there are a lot of things that we haven't got the data to back up our instincts, for want of a better word. So I think some of the things that we really need to look at, we need to look at different loading conditions, simple things like continuous beams, high shear scenario. We don't have any information on that. The last bullet point here, I tend to think is one of the most important, which is true also for carbon steel reinforcement. But I think in light of the corrosion properties and the alkalinity, looking at newer concrete, so looking at concrete mixes that are replacing some of the cement with calcined clays or GGBS or fly ash or any of the other common cement replacement products that are hitting the market. That's a huge area that we really need to go back to zero and recalibrate all of our design performance data. So in conclusion, before I finish up, if I could leave you with some concluding remarks, I would say it's that stainless steel rebar shows a huge amount of potential. So my own bias, if you like, is always towards the structural behavior and can it actually provide a better solution? I think the second bullet point is maybe one of the most important. So in terms of the costs, the economy, which of course then links into the environmental costs also, that's where it can make a really, really big saving. And I think as design, certainly in Europe, it's, I'm sure the same in New Zealand, as designs become under more and more pressure to provide a long life cycle and a low maintenance and a low environmental impact solution, then stainless steel reinforced concrete can really come into its own, both in terms of direct savings and also, like I said, those indirect savings when things like bridges need to be shut down for rehabilitation and so on. But we need more performance data. We need more reliability information, and really we just need more research. I have some useful references here. I don't expect you to look at them now, but when the slides become available, you can have a look at these. A simple Google will tell you quite a lot, but there's some reliable sources on here. And with that, I will end my presentation. That's my last slide, and hand over to...
Thank you very much, Catherine, for your excellent presentation. Dear listeners, if you have any question concerning this presentation or about any nickel-related topic, kindly send us your question via our webpage. Once you enter www.nickelinstitute.org, you will immediately see the yellow banner Technical Help. Click on it, register, it's free of charge, and fill in your question. One of our experts will come back to you fastest. Thank you all for attending this webinar. We are looking forward to have you on one of our next webinars again. Goodbye.